Well, once again, we have a resistor with a cross-sectional area of A, a length of L, and resistivity of rho. So the resistance is rho times L over A. Now we've already seen what happens if we took two resistors and connected them together in series. We found that the equation for the equivalent resistance for resistors in series is exactly opposite the rule that we had for capacitors connected in series. Okay. Let's talk about resistors in parallel. So I might make a connection between two resistors by connecting wires to tie the ends together. And of course I need some wire so that I could connect all this to a battery if I wanted to. Well, regardless of the battery, here's two resistors connected in parallel with one another. Now, I haven't really changed the length through which current's going to flow. If some current made it into the junction at point A, then that current splits up. Some of the current takes the top path through resistor number 1. The remaining current takes the lower path through resistor number 2. These currents reconverge at junction B. So the current that flows onward from there, that current and that current have to be one and the same. Now, the ratio in which they split up depends on the ratio of R1 in comparison to R2. If those are two identical resistors, then we're going to expect that the current in the top half is I over 2, and the current in the lower segment is I over 2. But there's no guarantee that the two resistors are exactly equivalent. In any case, what I've done now by putting the two in parallel is I've effectively increased the amount of cross-sectional area through which the current can flow. And so it would make sense that the resistance decreases by adding more and more resistors together in this parallel kind of connection. So let's see if we can derive a generalized equation for the equivalent resistance of two resistors that are connected in parallel, and then we'll extend our results to apply to any number of resistors connected in parallel. So now we want to invoke Kirchhoff's Junction Rule. In our last video, we relied on Kirchhoff's loop rule. Here, we invoke Kirchhoff's Junction Rule, which, as described earlier, whatever amount of current is flowing through the battery, we'll call that I total, that reaches the junction at point A, and some of it splits off. So we have a current I1, and then the rest of it splits off. We have a current I2. This current I2 reaches junction B, as does the current I1, and when they recombine, they just become this total current once again. So the junction rule says the total amount of current flowing into any junction has to equal the total amount of current flowing out of any junction. And in this case, then, we can say I total is equal to I1 plus I2. Very simple. Now, if we want to picture the equivalent circuit, in other words, could I just have one single resistor that draws as much total current through the battery based on its value of equivalent resistance? Yeah, that's what we're looking for. Okay, so in this equivalent circuit, based on Ohm's law, we can say that I total would have to equal the voltage of the battery divided by the equivalent resistance. Now, I can also apply Ohm's law not to the equivalent value or the total value of current, but I can apply Ohm's law just to this one resistor, I1, has to equal the voltage across resistor number 1 divided by the resistance. Likewise, applying Ohm's law to the other resistor, the current we've labeled as I2 has to equal the voltage across resistor number 2 divided by its resistance. Now I want you to think about how the battery voltage, the voltage across resistor number 1, and the voltage across resistor number 2 all compare. Let's draw our symbol for ground. So we know the electric potential right here is equal to 0. The electric potential here is the same thing as the voltage of the battery, and that's the electric potential at this point. That's the electric potential at this point. In fact, the electric potential at point A has to equal the voltage of the battery, and the electric potential at point B has to equal the electric potential at point B has to equal 0, because there's just bare wire making the connection to ground. So the voltage across resistor number 1 and the voltage, well, I can even extend this point over to here, right? This is also the battery voltage, and this is 0. So the voltage across resistor 2, the voltage across resistor 1, and the voltage across the battery are all one and the same. Of course, this is a familiar concept. This is basically how we define parallel connections. Any devices connected in parallel must have the same voltage. So I really don't need to call this V subscript 1. I can just get rid of the subscript. In fact, even get rid of the subscript on the battery here. And the quantity we're referring to as V is the battery voltage. It's the voltage across resistor number 1. It's the voltage across resistor number 2. So we take this expression and substitute. The total current is the battery voltage divided by the equivalent resistance. The current through resistor number 1 is the voltage divided by R1, and the current through resistor number 2 is that same voltage divided by R2. So in this case, we can divide out V, and lo and behold, we find that 1 over the equivalent resistance is 1 over R1 plus 1 over R2. Now what happens if we add a third resistor in parallel? Then it's exactly as you would expect. So we could generalize and say the inverse of the equivalent resistance is equal to the sum of all the inverse values. If we limit ourselves to just 2 resistors connected in parallel, then instead of having an equation that solves for the inverse of the equivalent resistance, we can find a common denominator, invert both sides of the equations, and we'll find that for 2 resistors, the equivalent resistance is R1 multiplied by R2 divided by R1 plus R2. So if the first resistor is 1 ohm and the second resistor is 1,000 ohms, what would be the equivalent resistance? Well, 1,000 times 1 is 1,000. 1,000 plus 1 is 1,001. And so we get an equivalent resistance of 0.999, which is just slightly less than the smaller of the 2 resistors. And this is always the case when resistors are connected in parallel. The equivalent resistance will always be less than the smallest individual resistor that makes up that combination. And the whole reason why is because the more and more resistors we introduce in parallel in a circuit opens up more and more pathways for the flow of current, effectively reducing the overall equivalent resistance. Hey, as always, thanks for watching.